in this question, a person fires a bullet. So they fire the bullet from shoulder height. Let's say they're using a rifle or something like that. I don't need to draw anything better than that, and in any case, I can't. And the bullet is eventually going to come and hit the ground, something like that. I'm going to set photo 1 as being the instant that the bullet leaves the gun, and photo 2 as being an instant before it hits the ground. So maybe just a nanosecond after it leaves the gun and a nanosecond before it reaches the ground. I'm going to set upwards as being positive y and rightwards as being positive x. Now, let's write down all of the information that is known in this situation. We do not know the displacement in x. That's one of the things that we're looking for. But we do know that the bullet is going to fall by 1.5 meters because the person fired it from 1.5 meters above the ground. So this is going to be negative 1.5 j hat meters. The bullet was fired horizontally, so that means that the initial y velocity was 0. And we also know that it was fired at 200 meters per second. So the initial x velocity is 200 I hat meters per second. The final velocity is unknown. The acceleration is going to be the usual 0 I hat meters per second squared in x and negative 9.81 j hat meters per second squared in y. Because these are the standard values as long as you're on Earth, your axes point upwards, that's what makes this negative. And this isn't in any powered flight, so acceleration would be 0. And finally, there's time, which is unknown. So in this question, we're being asked for the time first and then for the displacement of the bullet. So let's go ahead and solve for that. We know the displacement in y, the initial velocity in y, the acceleration in y, and we're looking for the time. There's only one equation that weaves together all four of those quantities, and that's toolbox equation 2. So delta y is equal to v initial times time plus 1/2 acceleration times time squared. So delta y was negative 1.5 is equal to v0, 0, times time, unknown, plus 1/2 acceleration, negative 9.81 meters per second squared, times time squared, which is again unknown. 0 times t is going to cancel out. So we are left with negative 1.5 is equal to half of negative 9.81 is negative 4.905 times t squared. So that gives us t squared is equal to negative 1.5 over negative 4.905, which is going to work out to negative 1.5 divided by negative 4.905 is negative 0.306. So let's call it 0.31. And taking the square root of that is going to give us the time, 0.55 seconds. So that's the first part of this question, finding the time that's required for this bullet to fall to Earth. What about the displacement? Well, we know the time, we know the acceleration, we know the initial velocity, we're looking for the displacement. So delta x is equal to v initial times time plus 1/2 acceleration times time squared. So delta x is equal to v0, that's 200, times the time, which was 0.55, plus 1/2 times acceleration, 0 times time squared. But an acceleration of 0 is going to cancel out this entire term. So we're going to be left with 200 times 0.55. Which is 110.6. So that is the displacement of the bullet in the horizontal direction. 110.6 I hat meters. That's how far it travels before it hits the ground. This question involves a dart player. So we have someone over here who is throwing a dart at a dartboard, and the dart is going to leave their hand and it's going to slightly arc downwards as it travels because it's going to fall under gravity. I'm going to set photo 1 as being when the dart leaves our player's hand, and photo 2 as being the instant before the dart hits the dartboard, let's say a nanosecond before. So now that I've set the photo 1 and photo 2, I'm going to set my origin and my axes. Origin will be the point at which it leaves this person's hand. I will set upwards as being y and rightwards as being positive x. Now, let's write down what are all of the things that we know and all of the things that we don't know. There is motion in both x and y. We know that the displacement of the dart was 10 meters in x, since our character was standing, he was standing 2.4 meters away in x, and we don't know what it is in y. That's the thing that we are solving for. V initial is 10 meters per second in the x direction, and we do not know, we do actually know what it is in y direction. He threw it horizontally, which means that it was 0 in the y direction. V final is unknown in both directions. The acceleration is going to be 0 in x, that is the very familiar value for something that's in projectile motion, and negative 9.81 j hat meters per second in y, meters per second squared rather, in y, because this is falling under gravity and we said that upwards was positive. So this is falling, so downwards is going to be positive over here. And we want to solve for the displacement in y. So we have 3 pieces of information in x. So the first thing we're going to do is we're going to solve for the time, and then we're going to use the time in y to solve for the displacement there. Okay, so this is part A of the question. We know displacement, we know initial velocity, we know acceleration, we're looking for time. So the only equation that weaves together all 4 of those quantities is toolbox equation number 2. So delta x is equal to 2.4 is equal to v initial 10 t plus 1/2 acceleration 0 times t squared. This entire last term is going to cancel out. So we're going to be left with 2.4 equals 10t, which can be rewritten as t is equal to 2.4 divided by 10, which is equal to 0.24 seconds. So that's the time that it takes for the dart to reach the dartboard. Now what we have to find is how far does it fall in those 0.24 seconds. Again, we know time, we know acceleration, we know initial velocity, and we're looking for a displacement. So delta y is equal to v initial times t plus 1/2 a times t squared, because that's the only equation that weaves together these 4 quantities. Delta y is unknown, but v initial was 0 times a time, which we don't really need to bother about, this is going to cancel out anyway, plus 1/2 times acceleration, negative 9.81, times time of 0.24 squared. So 0 times t cancels, and we are left with 1/2 times negative 9.81 times 0.24 squared, which works out to negative 0.28. And this would be j hat meters. So this is how far the dart is going to fall from its original position. Now for part B, this is the answer to part A. This is how far the dart falls. Now for part B, the question was, what does this tell you about how real dart players would play? Well, a real dart player would compensate for this fall by aiming a little bit higher, because since this is going to fall under gravity, aiming it higher means that there's going to be an initial velocity, and that is going to need to be compensated for. It's going to compensate for the fact that this falls. So a slight upward throw is going to compensate for this fall.